We were going to talk about multi-agent reinforcement learning. So we will do a quick, very quick, extremely quick recap of reinforcement learning, just a few basics. I assume that most of you, and maybe you will tell me if I'm wrong, but I'm assuming that most of you followed some of the courses I have seen that talk about reinforcement learning in the single agent setting. So we have only one agent that is there. I think in some course about computer vision or machine learning, you have these basics. And also, we will not go into many details about deep reinforcement learning. Okay? Also because I think that you already had some knowledge of the basics, at the very least, of neural networks. And in the context of reinforcement learning, for what concerns the most these lectures, doing deep multi-agent reinforcement learning or non-deep multi-agent learning really doesn't matter. So this will be 2 lessons, and it will be an overview. The field of research is huge, as mostly any field of research within the umbrella of machine learning nowadays, so there is no chance that we touch every possible concept. This will be an overview, especially targeted at making you understand what are the additional challenges when you go from a single agent learning setting to a multi-agent learning setting. Okay, that's where most of the focus of the talk will be. So, first of all, a quick recap, some basics, what reinforcement learning is about. It is basically about teaching an agent to do something in an environment, to achieve some goal, to accomplish some task in an environment, which can be a physical environment if we plan to deploy our models in robotics, or in a recommender system, for instance, Amazon recommending products or stuff like that, or can be a purely virtual environment if we think about video games, but not only, stock trading, stuff like that. And as you may already know, you have an agent that performs some actions on an environment that change state. The environment can change state due to agent actions or due to some spontaneous transition. The agent can perceive some observation about the environment. This observation can be noisy, can be partial, we will see, or can be a perfect snapshot, let's say, of the environment state, and can perceive a reward, for which the agent does not know the exact way to get a reward. The agent only knows, okay, now I got a reward. So it can only sample from rewards as individual scalar values from a reward function that is unknown. And so the goal is usually a desired terminal state of the environment, and the reward should usually be crafted to measure the utility of the action. So how closer to the goal the agent became by doing a given action in a given state. This agent, this is a dog not by chance and not only because it's cute, but because the most easy metaphor we could use to understand how reinforcement learning works is what we usually do when teaching animals, when training animals. So we simply tell the dog something many times, stand up, sit down, roll over, whatever. We give it a prize, a treat, okay? When it gets the action right, sooner or later the dog will learn that, okay, to get the prize I need to sit down when I hear this sound. To get the prize I need to roll over when I hear this other sound, okay? And so basically the idea is simple. By repeatedly giving rewards or punishments in the case of a negative rewards, depending on the agent action, the agent will learn an optimal policy. That is an optimal behavior, hopefully an optimal behavior. So the optimal way to achieve a given goal. A big distinction in the reward scheme is between dense and sparse rewards. A dense reward signal means that more or less every action that the agent takes in every state gives some clue to the agent about whether the action has been useful or not to achieve the goal or to accomplish the task. In a sparse reward setting, instead, usually the agent gets the reward seldom. Okay? oftentimes only when the training episode, when the task is accomplished. So that's why it's called sparse. The agent samples few reward signals. So for the vast majority of its lifetime, the agent actually has not an idea of whether the action is taken as good or not. So this will serve us to elaborate on this formulation in the multi-agent setting. So what happens is that to formulate a reinforcement learning problem, meaning a single agent setting, usually you need a decision process model, which is another way to call what is commonly called an environment or even a game, depending on where your research background is. We will see that many terms have an equivalent in game theory. And a learning goal. That's what formulates completely a reinforcement learning problem. The decision process model is simply a transition model that dictates how the environment changes state depending on the agent actions or some endogenous transition dynamics. There are many of decision process models. Two of them maybe most known are the Markov decision process, which is the basic one, basically, upon which all other reinforcement and multi-agent reinforcement learning models are built on top, and the partially observable Markov decision process. So in a Markov decision process, the fundamental property is not by chance, the Markov property, the fact that the current reward, so the reward that the agent will get by executing an action in a current state, only depends on the current state and the action, not by the previous states, not by the history of the agent actions that led the agent to the current state. I don't care about the past states, I only care about the current one and the current action. Okay? I don't know if it's familiar to you, but this is similar to the properties in a Bayesian network for which to understand the distribution of probabilities of a given node, you only need the parents of the node, not the ancestors. If this is not familiar to you, simply forget about it. The partially observable Markov decision process is a Markov decision process in which there is a complication. The agent cannot perceive the actual state of the environment, which means all of the properties with absolute certainty that define the environment, but either can only perceive a portion of the environment. This is easy to see thinking about video games, where usually you have a field of view. For instance, in a first-person shooter or whatever, in a strategic game, you usually have a field of view, and beyond that field of view, you cannot see anything, you cannot perceive your enemies, your allies, whatever. Or it can also mean that the perceptions that you get from the environment are noisy. They can contain error. This is usually the case when your observation is acquired through sensors, for instance. Sensors can be wrong, can have a tolerance, whatever. So that is another way of defining this partially observable Markov decision process. This was actually, so to say, the difficult part of defining the reinforcement learning problem. You need to carefully think about your real-world problem and whether, for instance, the Markov property does hold or not. If it holds, you can hope to formalize your problem as a Markov decision problem and gain some additional benefits, some nice property. If it is not the case, then you need to find another formulation. What instead is quite easy for single agent reinforcement learning is to define the other half of the problem. That is, what kind of goal my learning process should have. In single agent reinforcement learning, the goal is always the same. You want to maximize the expected return. That is the future rewards that the agent can collect from a given state onwards. So let's assume that you are at the beginning of the game, at the beginning of our Markov decision problem. We just started this reinforcement learning problem. The goal of every reinforcement learning algorithm is to make sure that the agent maximizes the accumulated reward. Okay? let's try to get the highest reward possible at each decision point. This is expected, maximize the expected return, because the function that assigns rewards from state action pair is not constrained to be a deterministic function. It can be a probabilistic function. So you can be not sure about the kind of reward you get. So that's where this statistical expectation comes from. The return is simply defined as the sum of all the rewards during the agent lifetime. And I guess you are already familiar with, again, how to calculate the expected discounted reward, where the discount is just, let's say, a mathematical trick to have non-terminating MDPs not explode the algorithm, basically. I think you are already familiar with Bellman optimality equations that are a simple way to estimate what is the optimal action in any given state and for any given action. And then the optimal policy is simply to always choose the best action I can. This is usually called a greedy policy. So the intuition, just to do a quick recap, the intuition, let's forget about the formula, but the intuition is simply that I can compute for any state in which I am the reward that I can expect from the state onwards. For any state I can transition to, I simply iterate the same reasoning. So, okay, if I do this action and I end up in that future state, what reward can I expect to get? And so on and so forth, until you get to a termination state and that your recursion finishes. There is a caveat. To do so, you need to know the MDP. Because I need to know, okay, if I go into that state, I've never been there before. If I go into that state in the future, what is my expected reward? I need a way to calculate it. So I need to know, in particular, the transition function of the environment, how to change from state to state, and the reward function. This is something that usually we don't have in reinforcement learning. So dynamic programming is not reinforcement learning. Okay, this is a sort of analytical solution. You can compute it. There is no learning in dynamic programming. You need to know the state transition of the environments, the function that defines the state transition, the MDP, or DP or MDP or whatever, and you need to know the reward function. If you know all of this, you don't need to learn anything. You can compute a solution. Okay? Maybe a question will be if computing such a solution is feasible or not, computationally speaking, so in terms of resources. But in theory, you can compute a solution. You don't need reinforcement. The real challenge comes when you do not know the MDP. And usually, in fact, in reinforcement learning, you assume that the state transition function and the reward function are unknown. Please notice that knowing the reward function or simply perceiving a reward signal are two quite different things. Knowing the reward function means that I already know for each state, given a given action, what reward I can get. Sampling a reward signal only means that for the state I have already been in and for the action I have already taken, I know that I sampled a scalar value. I know nothing about the reward function. I can try to construct it. That's called inverse reinforcement learning. It's another thing, but in general, I know nothing about the reward function. Again, for the state transition, it's the same. I have no idea, given a certain state I'm in, what state I will end up to when I do an action for the first time. I have no idea. I don't know the state transition function. Here is where reinforcement learning actually happens. Temporal difference learning is a family of algorithms that are usually the first algorithm you study. And the problem is that in the Bellman optimality equations, We know where we want to get. We know how to compute all of these values. Okay? And I simply can measure the error in estimating the reward I can get. Because I can estimate a given reward, then do the action, perceive a different reward, and correct the error. If I know the NDP, this is similar to supervised learning. Okay? I have knowledge of the ground truth of the MDP. The problem is that in usual reinforcement learning and in temporal difference learning is that you can't estimate the error because you have no idea about the NDP, about, okay, I did this action, I expected this reward, but instead I got this one. So what you do usually is that you have an update target, which is a substitute function that serves you to estimate the value of being in a certain state, the value in terms of the expected reward from the state onwards, or the value of doing a specific action. And here you can adopt this learning rate to establish whether learning is to be slower or faster, and all the caveats that are therein. An example of temporal difference learning is Q-learning, is very famous. SARSA is another, maybe slightly less famous. Q-learning is a very famous example. This is the Q-learning update rule, basically. That can be implemented. We will see it, like in less than 10 lines of Python code, for instance. So it's very easy to implement Q-learning. And this is basically a very quick recap of single agent reinforcement learning. Okay, so there is one agent that learns by repeatedly interacting with the environment. That's it. Now, what are the additional challenges when we go multi-agent? What does it mean to go multi-agent? Why should we go multi-agent if it is more difficult? Okay, so first of all, going multi-agent actually looks like this. No, not very difficult from this slide. It seems quite simple. Just add more agents. Okay, you have many agents that perform actions on the environment. Actions can be simultaneously carried out, can be in sequence. This may depend on the specific problem you are dealing with. Every agent perceives an observation, a reward, so this is the same as in single agent reinforcement learning. But here the additional thing is that all the actions combined have a combined effect on the environment. So what is called usually the joint action. Okay? Let's simply assume that I have two software agents that control the temperature of a room. One agent is in charge of opening and closing the windows. One agent is in charge of toggling on and off the air conditioning, the heater, and whatever. If you are as now in winter and the agent in charge of the temperature turns on the heater and the agent in charge of the windows open the windows, probably their joint effect on the environment will be none. Okay, they cancel each other. So this apparently simple thing gives rise to a lot of additional challenges. First of all, since there are additional challenges, we trust you. Why going multi-agent? Okay. Well, here there are a few motivations. I roughly separated in two groups. So one more on the multi-agent side. So the question is, why should we care about doing reinforcement learning but with multiple agents? And the other on the reinforcement learning side, which means basically why it may make sense to use multiple agents to do reinforcement learning. So on the multi-agent side, the benefit of going multi-agent reinforcement learning is that you can decompose a problem in sub-problems. Okay, the same reason why you have already seen with Professor Zambonelli why going multi-agent, why going distributed in other domains. Okay, so basically divide and conquer. Okay, let's decompose the problem in smaller problems and give each of the sub-problems to a different learning agents. That's fine. Sometimes centralization may be unfeasible. You can have different processes, connectivity issues, so you cannot simply push all the data to a central site. Some problem domain is inherently distributed. I'm working with independent robots. There is nothing I can do. I must, if I want to employ reinforcement learning, I must employ multi-agent reinforcement learning. Okay? Why instead to put reinforcement learning in multi-agent system? Well, for instance, it may be not trivial for a multi-agent system to define a behavior for each agent to achieve a collective goal. And so we may wish to let agents learn the behavior to achieve a collective goal. The environment, the place, virtual or physical, in which we deploy the multi-agent system may be partially unknown when I'm designing the system, so I cannot possibly enumerate all the situations. Okay, so these are just a few of the reasons why it may be worth to face the additional challenges of multi-agent systems. Just as a quick mention, okay, maybe I convinced you that it's useful to learn something in a multi-agent system, but why reinforcement learning? Are there any other approaches? Well, there are actually. Evolutionary computation, swarm intelligence. Reinforcement learning suits quite well rational agent systems, so the kind of agent system you studied up to now. You have a rational decision, or at least you should have a rational decision. The policy is based on a reward function that is akin to a utility function. Okay. We have what is called a situated action. The action that the agent takes depends on the context, on the state of the environment, and you have some sort of autonomy, in the sense that the only weak form of supervision that the agent gets is simply a reward scheme. Okay, so you don't have actually someone that tells the agent what to do. You have someone that tells the agent, okay, you are going in the right direction. So that's simply, it happens that reinforcement learning is well suited for multi-agent systems. But these are other approaches that can be relevant. Okay, is it true, I mean, that this is the case? I mean, are there real world systems that will benefit from this kind of stuff? Yes. Robotic were a few examples, okay, non-exhaustive list. Robotic warehouse management, learning optimal path, placement of items in video games. There are already video games that exploit the weakness of the player, okay? They learn to take advantage of the player mistakes. Cooperative autonomous driving. This is quite a hot research topic now because for many years the focus of semi-autonomous driving has been, okay, let's place a car in a street in a safe way, okay? This is debatable, but now that more or less we can put a semi-autonomous driving car in the streets, another question arises, okay, now what if there are multiple autonomous cars, semi-autonomous cars, okay? And so that's this cooperative driving. But it was one nice, a little of digression, one nice, I can't remember if it was a paper or something, but a few years ago it turned out that the main problem with autonomous cars, one could imagine, I don't know, that they don't recognize signals, the traffic signals, they need perfectly marked roads, this is all true. But one of the biggest issues with autonomous driving vehicles was that they were overly cautious. And they were extremely easily to get into a deadlock situation, like for instance where nobody crosses an intersection because everybody's waiting for someone else to make the first move. That was quite a nice paper, had a bit of resonance. Automatic trading in finance, this is already there since many years. Possibly it was one of the first real applications of reinforcement learning. Most of the financial trading nowadays is done without humans in the loop. Recommendation systems, another nice example. What's here? Let's see if some random noise starts. These are some links to some nice example you can have. This is, I don't know what's happening, but anyway, you have the links. So you have hide and seek is more of a toy scenario, but it's quite impressive. It is a bit of a commercial, so don't trust everything you see, but it was a very nice example, had a lot of resonance in the research communities. One example is about cooperative driving. One is a competition about robot soccer that is more or less every year in the context of I don't know which conference, but it is repeated every year. If you have questions, please feel free to interrupt me anytime, okay? Just raise your hand or just start speaking. Let's assume I convinced you that it is worth to do multi-agent reinforcement learning. Why? I will try to clarify for basically the rest of the slides, or the whole 2 lectures, about being careful of a few things. So, at some level of abstraction, the only difference between single agent reinforcement learning and multi-agent reinforcement learning is the number of agents. Okay? Usually more than one. Would be better more than 2, actually, because 2 agents is a kind of a peculiar case that usually you can deal with game theory alone. So this simple structural difference actually entails many problems. First of all, non-stationarity. In reinforcement learning with a single agent, state transitions of the environment only depend either on the dynamics on the environment, the spontaneous endogenous dynamics the environment may have, I don't know, it starts raining, and on the actions of the only agent that exists. That's it. If the agent is performing an action, and let's say nothing changes in the environment, the agent knows that it is its fault. Okay? Either I did something that was not effective, or something in the environment is preventing me to successfully bring about this action. In a multi-agent system, the environment is shared, okay, amongst many agents that are all acting together. Maybe not simultaneously, but in turns, whatever the case. They are all acting in the same environment. And as for our example before about the room temperature, they can hinder each other. Their actions can cancel out in the global vision of the joint action affecting the environment. So, each agent actions affect the other agent's observations. So the environment transition may change over time. And this is the definition of non-stationary. Okay? One of the biggest assumptions in single-agent reinforcement learning algorithms is that the environment dynamics are stationary. It means that they can be probabilistic. It can be that not always when I do action A in state S, I get to the reward R. It can be. But the probability of getting to a different reward stays constant over time. This is what stationary means. In multi-agent reinforcement learning, this is not the case anymore. Simply because maybe we are 2 agents that want to pick an item from a shelf, and it makes sense to have multiple agents because the warehouse is huge, so the first, maybe some agent is closer. We both go to pick the item. The second one that arrives doesn't find the item. Okay? The first time I am the second one, so I don't find the item, no reward. The second time I am the first, reward. The third time I am the first, reward. The fourth time I am no longer the first, no reward. So the probability of getting a reward may change depending on what other agents are doing. This non-stationarity problem means that the optimal actions and the optimal policies, so the optimal chain of actions that the agent can do to achieve a goal is not always the same. It can change depending on what other agents are doing. Okay? We are a number of agents that must collaborate to move a heavy object. My optimal actions depend on what the others are doing. For instance, if all other agents already picked up the item, I can do nothing and maybe I get the reward anyway, because they are doing the job. It's like in a group project, no? Somebody works and somebody doesn't work. So the fact that the optimal action change with respect to what other agents are doing is called the moving target problem. And the easiest depiction is something that I guess happened to all of us, an awkward situation when you have to cross a corridor or a narrow passage with another people. Maybe you are in the sidewalk of the road and you start dancing, no? Okay, I avoid you on the left, but also the other guy avoids us on the right. So we start dancing. That's the moving target problem. My optimal actions that could have been either move left or right, doesn't care, as long as the other person goes straight, now change it. The other person too moved and we are still in the collision path. Okay? So that's the easiest depiction of the moving target problem. This is a huge problem caused by non-stationarity of the environment. Another problem is best seen, as I was mentioning, by thinking about group projects. In single agent reinforcement learning, I am sure that if the agent gets to the goal, who should I give the reward to? The agent. There is only one agent. Okay? Apparently, he did something good. So, he chosen some action in a good way, and I have to give a reward to the agent, the only entity that is acting in the world. In multi-agent reinforcement learning, there are many agents that act concurrently. Who should I give the reward to? Are we sure that all the agents contributed to the goal? This usually is more prevalent in cooperative scenarios, so in multi-agent systems in which the agents need to cooperate. But a similar formulation can be done also in competitive scenarios, okay? So, giving credit, so recognition for having achieved the goal in a multi-agent system is not trivial. And again, the metaphor is that of a group project. I hope not, but probably it happened to you during your academic career that you had to submit a group project and you had some dead weight, okay? Somebody that didn't almost nothing, but get the mark at the end, get the score. That's a credit assignment problem. How can we actually value more the contribution of people who actually worked instead of people who basically did nothing and free ride the other participants? So that's another problem. I have no idea why it's not working anymore. Let's do this. Okay? Okay. Another issue, the last that we will see, these are the three biggest issues, conceptual issues. Then there may be many technical issues, but we here focus on the concept in this overview. Is the issue of equilibrium selection. We will see that there are, again, we will touch some game theoretical concepts briefly. In single agent reinforcement learning, given an environment state, a state of the environment and an action, the reward is always the same. Okay, again, it may be probabilistic, but it doesn't change over time. It's stationary. We have the Markov property. Okay, so in multi-agent reinforcement learning is that each agent action may affect other agents. So, what does this mean? That focusing on one agent, let's call the ego agent, the agent out of the n agent that we are focusing on, that always does the same actions. It has a fixed policy. It is not learning anything. He can experience, this agent can experience different rewards because they depend on what others are doing. So the return, the expected return of each agent may change. If we run, for instance, multiple times, even the same policy. It depends. Okay? So, actually, we will see that in multi-agent reinforcement learning, the half of the problem that for single agent learning we defined as, okay, that's trivial. In single agent RL, we always want to maximize expected return, is no longer true. There are cases in which maximizing the expected return loses meaning. The expected return of who? Do we privilege some agents? The average expected return, that's another thing. The maximum expected return, we only care about getting to the maximum return. We don't care about how many agents get to the maximum. This depends on the actual problem you are solving, so it is not so easy to define the target. So these are the three main, let's say, issues, challenges that doing research in working with multi-agent reinforcement learning has with respect to the single agent case. So now in the two following, let's say, chapters of the slides, we will first define the decision model. So half of the problem. And in chapter 4, in section 4, we will define a solution. Okay, so the other half of the problem. Then we must be a little patient because only in section 5 we will start thinking about actual algorithms. But we don't care so much in these lectures about the algorithm. There are too many algorithms, so it doesn't make really sense in an overview of the field. So, as I already mentioned, MARL, multi-agent reinforcement learning, and game theory are deeply related. Okay, game theory is a lot older than multi-agent reinforcement learning. So, terminology in multi-agent reinforcement learning oftentimes borrowed from game theory. Here, I try to quickly approximate what the main differences are. Okay? Obviously, if somebody fond in game theory will come here, probably will kill me, but this is for the benefit of being clear without 10 slides to distinguish the two fields. So, game theory has been traditionally mostly developed as a mathematical economics theory, as you may know. So that's where the background of game theory is. And mostly focused on competitive scenarios, okay? Actually stemming from the economic point of view. Most of the emphasis is on some sort of provable properties of the solutions that we have, analytical solutions that we can compute analytically. Multi-agent reinforcement learning instead is basically a subfield, a cross between distributed artificial intelligence and machine learning. It doesn't have a clear focus about scenarios. You can use multi-agent reinforcement learning in collaborative, competitive, or even mixed scenarios. The techniques change, obviously, the specific problems change. And the emphasis is more on the computation of solutions. Obviously, in reinforcement learning, they do care if they can prove that a given algorithm converges to the optimal policy, obviously. But you have many algorithms that are simply used or designed without any theoretical proof, or with theoretical proof that are extremely difficult to comply to in real-world use cases. But you use them anyway, because they give you good solutions in a good time, for instance. Or they give solutions where nobody else could give you a solution. There is a bit of terminology mismatch. So, usually in game theory, we don't speak about agents, but we speak about players of a game. We don't speak about an environment, but we talk about a game to be played. We don't talk about reward, but of payoffs. and utility functions. And usually the policy, that is the function that decides which action to do in which state, is usually called a strategy. But they are exactly the same thing. Conceptually, they perfectly map one to each other. Okay? In recent years, there has been an effort by some researchers, one that I mentioned in some of the slides about evolutionary computation, which is CAR tools, tried to make more mappings between game theory and especially what is called evolutionary game theory, which is a sort of extension of game theory towards multi-agent reinforcement learning, actually. There has been an attempt, but otherwise you may find in the literature different problem formulations, or at least problem formulations that seem different, that actually are talking about the same thing. Okay, so that's a bit of a problem when you do research in this field, because you are not sure that two things are the same, but you feel that they are the same. So, what kind of games do we have? Since game theory is older than reinforcement learning, should we need to reinvent the wheel, to reinvent formulations, abstractions over real-world problems, or can we reuse some formulation from game theory? No, we can reuse some formulation. So keep in mind that, strictly speaking, in game theory, a game is defined as a model of multi-agent encounter in a given environment. So it is a model of two agents, usually in game theory, meet each other and play a game. Which doesn't necessarily mean playing a video game or a tabletop game or a rock, paper, scissors or whatever. Play a game will be, we meet and we need to take a decision. That's it. That's what it means, play a game. So that's why game is actually a synonym for environment. It's the same. We can easily define a few kinds of games. Matrix games are more or less the simplest form of games you can find with multiple agents. There are multiple agents, but there is only one state of the environment. What do I mean by one state of the environment? Does it make sense, an environment with one state? Well, think about rock, paper, scissors. The game has only one state. You throw either rock, paper, or scissors. That is, you do one action, and the state of the game is your action and your opponent's action, and that's it. There are no other states. These kind of matrix games can be defined as zero-sum games if the sum of rewards is always zero. This means that the game is strictly competitive. If I win, you lose. We cannot win both. We cannot lose both. Okay? They can be common reward games. All agents get the same reward. These are fully cooperative. Or they can be general sum, whatever reward function. Then you can have another class of games which are called stochastic games, matrix games, but there actually are more states in the environment. The easiest example I could think of is tic-tac-toe. Okay, tic-tac-toe is the how to call it, the three crosses, the three circles that you have to cross. There are game states. The board of the game, okay, the 3x3 square of cells, is the board and the state of the game. If I write a cross somewhere, the state changed, and if my opponent draws a circle somewhere else, the state changed again. So the environment has multiple states. The game has multiple states. And then there are extensive form games which are peculiar because agents act in turns instead of simultaneously. And this simultaneous action is for the vast majority of the other games. So extensive form games usually are an abstraction of board games or card games where you play in turn. These are just examples. Many more formulations exist, okay, but we don't really care. This is just to give you an intuition of what kind of abstraction you can have. So for instance, rock, paper, scissors is a zero-sum matrix game. This is basically, how to call it, is a made-up game. It is not an actual game. It has been made up to study the problem of common reward games. So the rewards are always the same. They must cooperate if they want to get the reward. And the prize and F dilemma is probably the most famous example of a general sum game. Okay, I guess these things are not new to you, but probably you already have seen this with Professor Ramonani. Thank you. Then there are also stochastic games. For instance, cooperative Pong is a common reward stochastic game. Here in cooperative Pong, basically the goal is for these two things to bounce the ball endlessly. So they need to cooperate, fully cooperative. Level-based foraging is again a made-up game that can be both common reward or general sum. Here, the game works that you have multiple agents, they need to collect apples, but apples and agents have a level. They can only collect apples of a lower or equal level. And to level up, they need to collect more apples of the lower level. So this is a sort of made-up game. So even though multi-agent reinforcement learning in theory may have some common ground, there are some peculiar differences that we highlight now. A first difference is about the environment dynamics. Keep in mind that all of these things are not really crisp, are not 100% sure, because obviously game theory, as all research field, is evolving. So as soon as reinforcement learning came, some researchers in game theory started looking at reinforcement learning, and the two fields basically cross-fertilized each other. So for instance, evolutionary game theory is again an extension of a traditional game theory that goes somewhat in the direction of learning. So these are to quickly understand the main difference, but almost always you can find a specific niche research topic in game theory that instead falsifies this kind of claims. But traditionally in game theory, the environment only changes as a consequence of agents' actions. Okay? It is not the case that in game theory, usually in game theory, the environment changes by some endogenous dynamics. Only agents can change the environment. In economics, for instance, this is most of the kind of problem. Instead, in multi-agent reinforcement learning, the environment can have its own dynamics. So it's more general in a sense. Another really big difference is observability. Traditionally in game theory, the agents know everything of the game. They know, for instance, their payoff matrix. They know the utility function. Knowing the payoff matrix, this thing, what is the equivalent in reinforcement learning of knowing the payoff matrix that we said usually we don't have in reinforcement learning? This is equivalent to having knowledge of the reward function. I know what action I need to do to achieve a given reward. So that's quite different. But as we said, in multi-agent reinforcement learning, typically there is minimal knowledge of the game. Usually the reward function is unknown. My reward function as the ego agent, and also the reward function even more of the other agents. Keep in mind that every agent could have even a different reward function in principle. The state transitions of the environment, I have no idea. The observation functions of other agents. It may be the case that not every agent perceives the environment in the same exact way. And I don't know, in principle, how other agents perceive the environment. The action space not of the ego agent, but of other agents also, can be unknown. Even the number and the identity of the other agents can be unknown. This is quite peculiar of multi-agent reinforcement learning. In fact, here is where game theory and reinforcement learning developed somewhat independently, but moving in the same conceptual framework. We define the matrix game, no? Stemming from game theory. N agents, one state. Well, the MDP in single agent reinforcement learning is one agent, m states. It's a bit of a complementary, okay? Then you have the stochastic game that is a more general case of both, because you have n agents and m states. But for instance, in stochastic game, the game is fully observed. This is different from partially observable Markov decision process, in which you have one agent, m states, but it is partially observed. And its evolution to n agents, which is called decentralized partially observable Markov decision process, in which you are partially observable, m states, but you have n agents. So these things have been mostly developed in reinforcement learning. These things have been mostly developed in game theory. The more general category of both, that is the partially observable stochastic game, n agents, m states, partially observed. Keep in mind that here you have common rewards, okay? Only common rewards. No zero-sum games, no general sum games. Why? Because reasons. Because the first thing that came to mind to somebody to abstract away a specific problem apparently was in a common reward set. So this is called POSG, partial observable stochastic game. To some extent, it is the most general game. What is an example of this most general game? Well, many practical problems, unless you made some simplified assumptions, are of this kind. And for instance, one well-known benchmark in multi-agent reinforcement learning is a SMAC, which I think it's StarCraft Multi-Agent Challenge, which is based on a video game, StarCraft. Some of you may know the game. It is a micromanagement game. I don't know how to call them. I'm out of the loop since a few years, unfortunately. But it is a game in which you have to build buildings, you have to build the buildings, make units, and with units you need to fight other people. Obviously, this is just one example, okay? Another kind of n agents, m states, partial observer game is, well, soccer, to name one. Basketball, I mean, you can argue that some players have full observability over the environment if they are very good, but in the general case, they have a field of view to abide to, okay? And many other practical problems. The last difference that we mentioned between game theory, I think it's the last, yes, it's the last. Actually, the last difference we mentioned, again, not because this is the last, effectively the last difference, just because it is the last big conceptual difference, okay? We care about concepts, not technicalities, is communication. Usually in game theory, you assume that the players cannot communicate. Like, for instance, in the cornerstone of the prisoner dilemma is that the prisoners cannot communicate. In multi-agent learning, usually in a whole subfield of multi-agent reinforcement learning, agents do not communicate. But actually nothing really hinders communication. So the action space can include communication actions. And we will see later on, and this is actually my specific research interest and also mine with Professor Dambonelli, there are a few ways in which you can consider communicating in a multi-agent reinforcement learning scenario. So we will see in later slides. This is another big difference with respect to traditional game theory, in which the players are not expected to communicate. So let's do a first pause, a refresher. Here we defined the problem. This kind of POSG, PONDP, matrix game, they are ways to define the decision process, to formulate mathematically in an abstract way the problem you are dealing with, half of the reinforcement learning problem, the environment. After the pause, instead, we will try to characterize the other half, the solution. That in reinforcement learning was easy, maximizes pet return. Here, not so much. Most of these concepts, I think, you should already be familiar with because they stem almost always from game theory.